Hello everyone, so in this video we'll be talking about X-ray diffraction. X-ray diffraction is a technique which is used to measure distance between atoms within a material and also determine the crystallite size. This technique exploits the wave nature of light, and this technique was invented by Sir William Henry Bragg and his son William Lawrence Bragg, and they were awarded Nobel Prize for this. So if you have a material like this and if you look under the electron microscope, you'll see that it has different crystallites shown by the the blue borders, and within each of these crystallites you have atoms arranged in a specific way. And so this technique is basically used to determine the distance between the atoms within each of these crystallites and also determine the size of these crystallites. So this technique is actually based on something called Bragg's law. So if you have, according to Bragg's law, when you have two atomic planes as shown by the black lines here, and when X-rays interact with uh, these two planes as shown in this figure here. So here you have two waves, the red wave and the green wave. So when they when they interact with these two planes of light, the X-rays in this case are very small compared to that of the distance or the size of the atoms over here. So they undergo elastic scattering. In other words, they X-rays reflect and they don't undergo any energy loss. So when these reflected rays are reflected from the atomic planes, they undergo constructive interference, and depending on how they undergo the constructive interference, and depending on the number of planes which are oriented in the same direction, you can get the signal of intensity versus the angle swept. So uh, by looking at this geometry for the theoretical point of view, so when the two rays of light interact with consecutive planes, they kind of form this geometry where there are two right angles. So now mathematically, if you consider this distance CB and BD, it is actually the additional distance or the path length that is being traversed by the green wave compared to that of the red wave. So if you want to calculate this, you can do some basic trigonometry as shown from this figure on the side here. So this path length is path length, CB and BD are equal to lambda by 2. This is because you can see that there is one trench and one peak, and you know that distance between two consecutive peaks is lambda. So the distance between one trench and one peak will be lambda by 2. And also mathematically, from this right triangle here, the distance BD is in terms of the atomic plane distance is d sine theta. So now if you substitute that and use this trigonometry, you will be able to get that the additional path length that is traveled is lambda, which is equal to 2 times d sine theta. This has actually been generalized to 2d sine theta is equal to n lambda, which is known as Bragg's law. Now let's see where this n comes from. So when you consider just the consecutive planes like plane 1 and plane 2 as shown here, the light, the additional path length that is traveled by the light by the second wave is lambda by 2 plus lambda by 2, as we discussed in the previous slide. When you sum it up, you get lambda is equal to 2d sine theta. However, you can also consider plane 1 and plane 3, which is, you know, which also undergoes constructive interference. But in this case, the light travels the additional path length of lambda plus lambda or 2 lambda. Similarly, you can consider the any of the two planes, and when you try calculating the path length, you can kind of keep doing this, and eventually when you consider plane 1 and the plane n plus 1, you'll figure out that the additional path length traveled is n lambda, and that will be equal to 2d sine theta. So this is why this has been generalized, and this is how the n comes from. So now XRD tools are quite complicated tools. As you can see here, this is a Rigaku Ultima 4, and basically they have this X-ray source on the left, and then they have uh, a detector on the right, which captures the reflected X-ray. So basically, when you are doing the experiment, you have a source of X-ray, and then you either turn your sample or your detector, and then when you do so, and when the X-rays undergo constructive interference, you will start seeing peaks only in those directions. And using this X-ray intensity versus 2 theta, you can actually calculate some useful information. So let's see how to do that. So this is an example data. So the data that you're seeing here is intensity on the y-axis and 2 theta on the x-axis. So the peaks that you're seeing are corresponding to the different planes, and the more intense and the narrow the peak is, that means more of these crystallites are present within the material. And uh, and uh, basically, as I mentioned before, you have to keep in mind that this technique is slightly different from XPS. In the case of XPS, you use ALK alpha X-ray or MGK alpha X-ray, and if you look at the wavelength of these X-rays, they are about between 8 and 10 angstroms, which is more or less size of the atom. So when these X-rays undergo interaction with the material, they actually undergo inelastic scattering, or the uh, they undergo energy loss when they interact with the material. However, in the case of CUK alpha, the wavelength is much lower. It's only 1.5 angstroms. So when these interact with the atoms, they undergo elastic scattering. So in XPS, the data that you collect is the intensity is actually the number of photoelectrons that is emitting from the material. But in the case of XRD, it is actually the X-rays that are reflected from the sample. So that is the difference that you should keep in mind. And depending on the planes that reflect the X-rays, you can see peaks corresponding to the different planes. As you know, a material can have uh, the atoms oriented in different directions. So in XRD, we are actually, one of the things that we are interested in calculating, other than the interatomic spacing, which can be calculated using Bragg's law. You have something called a Scherrer's equation, which is used to determine the crystallite size. To remind you what crystallite size is, as I mentioned in my first slide, you have atoms arranged in a specific orientation, and these can vary depending on the crystallites that they are present in. So the blue borders, these each of these borders is a crystallite. So using Scherrer's equation, you can actually determine the size of these, average size of these crystallites. So once you have the XRD, so I will actually be showing how the crystallite size is calculated. So D, in this formula, D is the crystallite size, K is Scherrer's constant, and this can vary between 0.68 and 2.02 depending on the nature or the shape of the crystallite. And lambda is the wavelength of the X-ray. As I mentioned before, the wavelength is 1.54 angstroms, and beta is something called full width half maximum. I'll be showing how to get this full width half maximum by doing some fitting in Origin Pro. And theta is the half angle. So we have 2 theta here, so we have a cos of theta. And by the way, when we are calculating the crystallite size, we need to convert beta and theta, which are in degrees, to radians. So let me switch over to Origin Pro in order to calculate the the full width half maximum. So this is the XRD peaks for zinc oxide. So I'm interested in calculating the crystallite size for the planes 100, 002, and 101. So now the way you do the fitting is you choose this uh, selection on active plot, and then you define the area. And so here you can actually move the to fit the correct peak. And then once you have selected the area, you can go to analysis, and then fitting, and then nonlinear curve fit, and say open dialog box. Might take a while before it opens up. And then under category, you keep it as origin basic functions, and then under function you choose Gauss. And here you can kind of see that the fitting that is being done. So you have the option to do one iteration wise, or you can do fit until converge. And then once you do that, you can say okay. Once you say okay, you'll see that the table of values has been plotted. And here the two of the values that are of interest for us is XC, which is the location at which the peak is present. So here 36.27, and W is the full width half maximum, which is something. So these are the two values that we'll be taking from this uh, fit and fit curves, the data that we have obtained from the fitting, and we'll be calculating the crystallite size. So similar to this peak, I have already done the fitting for uh, the other two peaks as well. So we have three peaks now, and so we have three full width half maximums, and we have the position of each of these peaks. And I have summarized this data in the table here, the peak position and the full width half maximum. And then I substitute values. Here I'm showing an example for just the first peak, or the peak at 31.87. So when you correctly substitute the values, and you can get the crystallite size. And you can see that for all of these orientations or these planes, the crystallite size is more or less similar. And as I mentioned before, keep in mind that beta and theta are in degrees when you collect the data, and they must be converted into radians when you do the calculations for the crystallite size. Yeah, that's about it.